Day 1. Mars. You wake up and the first thing you notice is not the light. It is not the cold. It is a sound. A low, steady hum coming from somewhere in the wall behind your head. The life support fan. It runs every second of every day, pushing recycled air through a filter, scrubbing out the carbon dioxide your lungs just exhaled, pumping oxygen back in at the exact pressure your blood needs to carry it. You have never noticed that sound before. Back home, you never had to. Back home, the air was just there. Here, if that fan stops, the silence that follows is not peaceful. It is a clock starting. That is the thing about Mars that nobody says plainly in the press conferences and the launch celebrations and the animated videos of glass domes catching the pink afternoon light. Mars is not trying to kill you. It does not hate you. It does not even know you are there. Every single system keeping you alive right now knows that better than you do. And every single one of those systems was built by human hands, which means every single one of them will eventually need human hands to keep it running. The question was never whether we could build a rocket big enough to get here. The question is whether we can keep Earth alive inside a machine. And the answer to that question is a lot harder than any launch sequence ever showed you. There is a moment in Percival Lowell's career that tells you everything about the way human beings think about Mars. It is 1894. Lowell is a wealthy Boston astronomer with his own observatory in Flagstaff, Arizona, and a conviction so strong it might as well be religion. He believes Mars is covered in canals, not natural formations, canals, built things, evidence of a civilization so advanced it had already solved the problem of planetary water scarcity and was moving liquid from the poles to the equator through an engineered network spanning an entire world. He drew maps. Detailed, beautiful maps. He gave the canals names. He published books. He lectured to packed halls. And for a generation of Americans, the question was not whether intelligent life existed on Mars. The question was what they were like and whether they were watching us back. Lowell was wrong about every single detail. There are no canals. There never were. What he saw through his telescope was a combination of real surface features, optical artifacts, and the brain's remarkable ability to connect dots into patterns that confirm what it already believes. But here is the part worth sitting with. Lowell was not a fool. He was educated, meticulous, and passionate. He built an entire observatory dedicated to studying a single planet, and he still saw what he wanted to see instead of what was actually there. That instinct did not die with Lowell. It just got better clothes. By the time H.G. Wells published The War of the Worlds in 1898, the cultural template was already set. Mars was a place with history, a neighbour, not a rock. Wells flipped the premise and gave us Martians who came to us instead of us going to them. But the underlying assumption held Mars was the kind of place where civilization was possible. Then the space age arrived and the canals disappeared under orbital photography. And we let go of the Martians but kept the dream. Because the dream was never really about them. It was always about us. By the 1960s, Mars had become the answer to a very American question. The frontier was closed. The continent had been crossed, settled, and subdivided. The moon was being claimed. What came next? Mars came next. It was right there in the cultural bloodstream, obvious and inevitable. The next line on the Manifest Destiny map. And then Andy Weir wrote The Martian, and something remarkable happened. A book about a man stranded alone on Mars, growing potatoes in his own waste, became a global phenomenon, not because it was terrifying, though it was, because it was hopeful, because Mark Watney looked at an uninhabitable desert world with an atmosphere that would kill him in 90 seconds and said, essentially, I am going to science the heck out of this, and audiences around the world stood up and cheered. That movie made Mars feel solvable. It made the gap between where we are and where we need to be feel like an engineering problem, with a clever solution waiting at the end of a third act. And then SpaceX started releasing animations. If you have ever watched a SpaceX Mars animation, you know exactly what I mean. Starships arcing through a coral sky, glass domes catching afternoon light, people in clean suits walking between modules that look like something between a research station and a well-designed airport terminal, children running in open spaces, greenhouses full of actual green, everything orderly, bright, and self-evidently worth doing. Those animations are not dishonest. They are aspirational. They show a destination, not a path. They show what might exist after every single problem has been solved, which is a fine thing to show if you are trying to inspire people, and a dangerous thing to mistake for a plan. Here is what those animations never show you. They never show the first year, the year before the domes, the year before the greenhouses, the year when the question is not whether Mars can become beautiful, but whether the people who went there first can survive long enough to find out. They never show what it costs to replace the things that Earth gives away for nothing. Here is a fact worth holding on to. Every single frontier that human beings have ever settled, from the steppes of Central Asia to the islands of the Pacific to the American West, was still on Earth. The air was already there. The water existed somewhere nearby. The soil, however poor, could grow something if you worked it right. The gravity kept your blood where your body needed it. Even the harshest place a human being has ever survived on this planet came with a set of planetary services running silently in the background, free of charge, never noticed until they were gone. Mars does not come with any of that. Mars is not a harsh version of Earth. Mars is not a desert you need to water, or a cold place you need to heat, or a remote place you need to connect. Mars is a world where the background conditions that every living thing on Earth has relied on for 4 billion years simply do not exist. And the moment you land there, every one of those background conditions becomes a line item in an engineering budget that has to be paid every single day or people die. We did not study Mars and then decide it was reachable. We imagined it was reachable first. We imagined it with canals and civilizations and solvable survival problems and cinematic third acts. And that imagination has been quietly shaping what we allow ourselves to understand ever since. Every frontier in human history was still on Earth. Mars is the first one where Earth itself is missing, and that changes everything. On the 6th of September, 1620, a ship called the Mayflower left Plymouth, England, carrying 102 passengers toward a shore that none of them had ever seen. The crossing took 66 days. The ship was cramped, cold, and foul-smelling. 2 people died en route. 1 was born. By any measure of the technology available to that era, the voyage was a success. Then they arrived. By the following March, 45 of the 102 passengers were dead. Not from the crossing, from the winter, from exposure and starvation and disease in a place that had no infrastructure to receive them, no supply chain to sustain them, and no margin for error when the things they brought with them ran out or broke down or turned out to be the wrong things entirely. The ship worked. The ship did exactly what a ship is supposed to do. It crossed the ocean and delivered its passengers to the other side. What the ship could not do was make the other side ready. This is the thing about rockets that is almost never said clearly in any serious conversation about Mars colonization. A rocket is a delivery vehicle. It is a staggeringly impressive delivery vehicle. Arguably the most complex machine human civilization has ever attempted to operate at scale. And what SpaceX has done with reusability and cost reduction over the past decade is genuinely one of the great engineering achievements of the modern era. None of that is in dispute. But a rocket delivers. It does not build. It does not sustain. It does not decide what happens after the hatch opens and the passengers step out into a world that has been waiting for them without preparing for them. Ask yourself a simple question. If Starship achieved everything its designers hoped for, if it became fully reusable and cheap to operate, and capable of carrying 100 people and their supplies to Mars on a regular schedule, what exactly would those 100 people step out into on the other side? What is waiting for them? Right now. The honest answer is nothing. A pink sky and about 600 pascals of carbon dioxide, and a surface temperature that averages around -60 degrees Celsius and no structure. No power, no breathable air, no water extraction, no food production, no medical facility, no landing pad, no anything, just the planet, which does not care. Before a single human being can survive on Mars for more than a few hours, someone has to have already delivered and successfully operated a power system capable of running through dust storms and Martian nights that drop to -100 degrees. Someone has to have delivered and tested an oxygen production system that works reliably at scale. Not in a laboratory on Earth, but in actual Martian conditions, with actual Martian dust and actual Martian temperature swings. Someone has to have confirmed that a water extraction system can pull usable water from ice or regolith at the rate a human population requires. Someone has to have put in place emergency shelter with enough redundancy that a single failure does not kill everyone inside it. All of that has to work before the people arrive. Not during. Before. And here is where it gets genuinely difficult in a way that most timelines gloss over. All of that pre-positioned infrastructure has to be delivered in pieces, by robots and automated systems, and it has to operate reliably for months or years without any human being there to fix it when something goes wrong. Because something will go wrong. It always does. A power system that can diagnose its own faults and either correct them or fail gracefully without human intervention. A water extraction unit that can clear its own filters and manage its own mechanical wear without a technician. A communication array that can reposition itself after a dust storm without a person climbing up to adjust it. Every piece of that advanced infrastructure has to be not just functional but autonomous, because the people who could fix it are still on Earth, months away, and they cannot help. There is a word for what we are actually trying to build when we talk seriously about Mars colonization. The word is not mission. The word is not outpost. The word is not even base. Though base is closer, the word is system, a self-sustaining, self-repairing, continuously operating system that can keep human beings alive in an environment that will kill them within minutes if any part of the system fails. Starship is not that system. Starship is what delivers the pieces of that system. The rocket is the truck. The colony is what the truck is supposed to carry. And right now, we are spending an enormous amount of time and attention perfecting the truck, while the thing the truck is supposed to deliver barely exists outside a drawing board. The Mayflower crossed the Atlantic. It did exactly what a ship was supposed to do, but the people who stepped off it nearly died because the shore was not ready. A rocket can make Mars reachable. It cannot make Mars ready. The most impressive delivery vehicle in human history is only as useful as what it delivers, and what it needs to deliver to Mars, before any human being sets foot there, is something we have not yet learned how to build. Picture the last morning you spent somewhere you loved. Maybe it was a kitchen that smelled like coffee. Maybe it was a porch with a particular view. Maybe it was just a bed where you slept well. Now picture the moment you knew you were leaving and could not come back for a very long time. That feeling, that specific mixture of clarity and weight, is approximately what the crew of a Mars mission experiences about 3 days out from Earth. When the planet behind them has shrunk from a world into a marble, into a bright point of light that looks increasingly like every other bright point of light around it. Except they are not coming back in a long time. They are coming back in roughly 3 years. Minimum. If everything goes according to plan, and if something goes wrong between departure and arrival, they are not coming back at all. The journey to Mars takes between 6 and 9 months depending on the trajectory, the propulsion system, and the alignment of the two planets in their orbits. Earth and Mars only reach their closest approach to each other once every roughly 26 months. Miss that window and you wait. There is no shortcut. There is no other road. The physics are what they are, and the physics do not negotiate. What makes the corridor truly different from any journey human beings have taken before is not the distance and not the duration. It is one specific fact that changes the nature of everything else. Once a spacecraft passes a certain point on its trajectory toward Mars, turning around is no longer a practical option. The fuel required to reverse course and return to Earth exceeds what any realistic mission carries. The crew is committed. Whatever happens next, they handle it themselves. In low Earth orbit, where the International Space Station lives, an emergency still has an exit. If a crew member becomes critically ill, a Soyuz capsule can have them on the ground within hours. If a system fails catastrophically, evacuation is possible. The planet below is always there, close enough that its gravity feels like a safety net, even when it technically is not. On the way to Mars, that net disappears. A medical emergency at month 4 means the crew manages it. A serious equipment failure means the crew solves it. A psychological breakdown means the other crew members handle it. In a spacecraft smaller than most studio apartments, with no outside help arriving for months, and no guarantee it will arrive at all. The radiation environment in deep space adds a biological dimension to the journey that is easy to describe and hard to fully absorb. Once a spacecraft leaves the protective envelope of Earth's magnetic field, the charged particles streaming out from the Sun and the cosmic rays arriving from outside the solar system have nothing deflecting them. They pass through hull material. They pass through human tissue. They do not kill immediately. They accumulate, adding to a lifetime account of cellular damage that increases cancer risk and, based on animal studies, may affect cognitive function in ways researchers are still working to understand. A crew spending 6 to 9 months in transit arrives at Mars already carrying a radiation load that matters. Not a crisis. Not an emergency. A cost. A cost paid before they have done a single day of work on the surface. Before they have faced the dust or the cold or the equipment failures or any of the things that will define the mission. They spend their biological budget on the way there. And then there is the spacecraft itself. 6 people. A living volume roughly equivalent to a large recreational vehicle. 9 months. No possibility of stepping outside. No change of scenery. No fresh food. No natural light. No variation in the sounds and smells of daily existence. The same faces across the same table for the same meals. Day after day. Week after week. Month after month. Human beings are extraordinarily adaptable, but nothing in our evolutionary history prepared us for sustained confinement in a sealed metal tube with a small group of people and no exit. Studies from Antarctic winter over stations and from the Mars 500 isolation experiment in Moscow show a consistent pattern. Morale softens over time. Sleep quality degrades. Small frictions between crew members accumulate in ways that would resolve easily in a normal environment and do not resolve easily when there is nowhere to go. Every one of those studies had one thing a real Mars transit does not have: an emergency exit. Everyone inside knew the door could open if things went truly wrong. On a real Mars transit, the door does not open. If a crew member has a breakdown, the crew handles it. If a crew member dies, the crew keeps flying. The 7-month corridor is not the hard part of the mission. It is the part that teaches the crew, in the most visceral way possible, what the mission actually is. It is where Earth becomes a signal delay and a shrinking light. It is the point where going back costs more than going forward, and the only direction with any logic left in it is ahead. In August of 2012, a spacecraft called the Mars Science Laboratory entered the Martian atmosphere at roughly 5.8 kilometers per second. It had traveled 567 million kilometers to get there. Everything up to that moment had gone according to plan. What happened next was 7 minutes that the engineers who designed it described, without exaggeration, as the most terrifying sequence they had ever built. The spacecraft hit the atmosphere and began to slow. Friction heated the heat shield to temperatures approaching 1600 degrees Celsius. Parachutes deployed. The aeroshell separated. A rocket-powered sky crane fired its engines and lowered the rover on cables toward the surface. The cables cut. The crane flew itself away to crash at a safe distance. The rover, Curiosity, settled onto 4 wheels in Gale Crater and sent back a signal that took 14 minutes to reach Earth. The engineers in the control room did not know if any of it had worked until the rover was already either safely on the ground or scattered across the landscape. 7 minutes of autonomous operation, with no possibility of human intervention. 7 minutes, during which everything had to go right, because there was no recovery from anything going wrong. Curiosity weighs about 900 kilograms. A pressurized habitat capable of supporting 6 human beings for an extended stay weighs somewhere between 20 and 40 metric tons. A nuclear power reactor small enough to deploy from a lander but capable of powering a colony weighs several tons more. N. Ascent Vehicle, the rocket that would carry a crew back off the surface, weighs tens of tons fully fueled. A fuel production plant, a water extraction system, a greenhouse module, a medical bay, a communication array, a spare parts depot. When you add it all up, a minimally functional Mars presence requires delivering somewhere in the range of several hundred metric tons of hardware to the Martian surface, across multiple missions, over multiple years, and not just delivering it accurately, softly, and close enough to the other things already delivered that the pieces can actually work together. Mars makes this extraordinarily difficult in a way that has no clean analogy anywhere else in the solar system. The planet has an atmosphere. On the surface, this seems like it should help. Atmosphere means aerodynamic braking. Atmosphere means parachutes do something useful. Except the atmosphere of Mars is about 1% the density of Earth's. It is thick enough to heat your spacecraft to plasma temperatures during entry. It is not thick enough to slow a heavy payload down to landing speed using parachutes alone. The sky crane system that landed Curiosity was a masterpiece of engineering, and it worked beautifully. For a payload under 1 metric ton, nobody has ever landed anything remotely approaching the scale of a crewed habitat on Mars. The proposals exist. The physics does not rule it out. But there is a very large distance between a proposal and a successful landing of 20 tons in a specific location on a planet that has never been paved, surveyed at high resolution, or prepared in any way. And then there is the question of precision. Even the best current landing systems have an accuracy measured in kilometers. A water extraction unit that lands 2 kilometers from the habitat means a 2-kilometer traverse in a spacesuit carrying heavy equipment, over terrain that has never been walked on, with no maps worth trusting and no rescue if something goes wrong during the traverse. Think about what a 2-kilometer mistake actually means in practice. The habitat is there, the power system is there, the oxygen system is running, but the water unit is over that direction, and the fuel plant landed somewhere to the north, and the emergency shelter is not where it was supposed to be. None of these things are catastrophically far. None of them are impossible to reach, but every trip between modules is a full extravehicular activity, a suit-up procedure, pressure checks, airlock cycling, oxygen expenditure, and the constant background risk of suit failure in an environment that will kill you in about 90 seconds without it. This is the scenario that almost never appears in the optimistic version of the story, a landing where everything succeeds and still creates a crisis. Not an explosion, not a catastrophic failure, just the quiet, grinding operational difficulty of a settlement where every piece of infrastructure is slightly not where it was supposed to be. And every day begins with a calculation of how much energy and oxygen and time you can afford to spend getting from where you are to where you need to be. Landing on Mars is not a destination. It is a diagnosis. It is the moment you find out whether the gap between your plan and your reality is small enough to survive. The 7 minutes of terror that the Curiosity team felt in 2012 will be felt again, for longer, with far higher stakes. When the first crewed Mars lander enters that atmosphere, the difference is that this time, if the diagnosis comes back wrong, the people receiving it will be the ones inside. Imagine a fire breaks out in a building downtown. Within minutes, trucks are rolling. Within the hour, 100 firefighters are working the scene, drawing from hydrants fed by a municipal water system, guided by a communications network, supported by a hospital system standing by for casualties. resupplied by a logistics chain that can put more equipment on scene before morning. The fire gets fought. The building may or may not survive, but the people inside have a chance because an entire civilization mobilized around them the moment the alarm went off. Now put that fire on Mars. The alarm goes off in Habitat Module 2. A seal on the oxygen line has failed and the pressure is dropping. The crew has roughly 4 minutes before conditions inside become dangerous. There are no trucks coming. There is no municipal system. There is no hospital standing by. There is no second team. There are the 6 people inside the habitat. The tools they brought with them, the training they received before departure, and the parts that are either already on Mars or are not available at all. That is the air problem on Mars, and it is bigger than it looks. The atmosphere of Mars is about 95% carbon dioxide. The surface pressure averages around 600 pascals, compared to roughly 101,000 pascals at sea level on Earth. That pressure is not just thin, it sits below the threshold at which exposed human tissue would begin to experience serious physiological distress within seconds. Without a pressurized suit or a pressurized habitat, a person on the Martian surface does not suffocate slowly. The process is faster and considerably less peaceful. So before anyone on Mars can eat, sleep, work, think, argue, fall in love, or do anything else that human beings do, 3 separate and interconnected problems have to be solved simultaneously, every single day, without stopping. The first problem is oxygen production. The only scalable source of oxygen on Mars is the carbon dioxide in the atmosphere, which can be split through a process called solid oxide electrolysis. A device called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment, demonstrated this on the surface of Mars aboard the Perseverance rover between 2021 and 2023. Across 16 separate runs, MOXIE produced oxygen from Martian air. The total amount it produced across the entire experimental campaign was enough to sustain one person for roughly 3 hours of normal activity. MOXIE was not designed to be a life support system. It was designed to prove that the chemistry works in actual Martian conditions, which it did, and that proof matters enormously. But the distance between proving that a process works and building a system that runs that process continuously, reliably, at scale, for years, in dust and cold and radiation, without a technician available to service it every time something degrades, is not a distance you cover by building a bigger version of the same box. It is an entirely different engineering problem. The second problem is pressure. The habitat has to maintain internal pressure high enough that human physiology functions normally. Every seal is holding back a pressure differential that wants to equalize. Every joint, every hatch, every penetration in the habitat wall, for cables or pipes or sensors, is a potential leak point. On Mars, a slow leak is not a minor maintenance issue. A slow leak is a budget. Every day it continues. Your margin gets smaller. The third problem is carbon dioxide removal. Human beings exhale carbon dioxide constantly. In a sealed environment, it builds up. At low concentrations, it causes headaches and impaired judgment. At higher concentrations, it causes rapid unconsciousness. The systems that scrub carbon dioxide from habitat air are not optional equipment. They are as essential as a heartbeat, and they require consumable materials that have to either be resupplied from Earth or manufactured locally, and they produce waste products that have to go somewhere. Here is the thing about these 3 problems. They are not 3 separate problems. They are one problem made of 3 parts, all dependent on each other, all dependent on power, and all vulnerable to the thing that gets into everything on Mars, which we will come to shortly. Pull on any thread and the whole fabric moves. On Earth, none of this requires any thought at all. You open a window, you step outside, you breathe. The oxygen you are breathing right now is the product of 4 billion years of photosynthesis by organisms ranging from ancient cyanobacteria to the tree outside your window, maintained by an atmospheric system so large and so old and so thoroughly self-regulating that it will not notice if every human being on the planet holds their breath for a minute. You have never paid for air. You have never serviced the machine that makes it. You have never worried that it would fail during the night while you were sleeping. On Mars, someone will worry about that every night. Someone will check the logs before they sleep and check them again when they wake up. Someone will know exactly what the oxygen partial pressure was at 3 in the morning, and exactly what the carbon dioxide concentration was at 5, and exactly how much consumable reserve remains in the scrubbers and exactly how long, before those reserves run low, if the primary system cannot be repaired. Day 200. The primary carbon dioxide scrubber is running at 83% efficiency. The diagnostic system says everything is nominal. The filter was replaced on schedule. The power draw is normal. The output is not. 2 options. Open the system and try to diagnose the problem manually, which means taking it offline, which means the backup carries the full load, which means the margin just got very thin, or leave it running at 83% and hope it stabilizes, which means accepting that the buffer is smaller than protocols require, which means if anything else goes wrong in the next 72 hours, the options start narrowing fast. There is no third option. There is no supervisor to call. There is no replacement unit sitting in a warehouse across town. On Earth, air is weather. On Mars, air is hardware, and hardware breaks. Turn on a faucet, not metaphorically. Actually picture it. The handle turns, the valve opens, and water comes out, cold and clear and immediate. You do not think about where it came from. You do not think about the reservoir upstream or the treatment plant that filtered out the things that would make you sick or the pumping stations that maintain the pressure in the pipes or the network of municipal infrastructure that connects all of those things to the fixture in your kitchen. You do not think about the engineers who design that network or the workers who maintain it or the regulatory systems that ensure the water coming out meets the standards your body requires. You think about water. You got water. Done. What actually came out of that faucet was the product of a hydrological cycle that has been running on this planet for roughly 3.5 billion years, captured and processed and delivered by a civilization that has been building water infrastructure for at least 5,000 years, regulated and maintained by institutions whose entire purpose is to ensure that when you turn the handle, something comes out. What came out of that faucet was not water. It was a civilization, in liquid form. Mars has water. This is one of the most repeated facts in every optimistic discussion of Mars colonization, and it is true. And it is also one of the most misleading truths in the entire conversation. Mars has water locked in ice deposits at and near the poles. It has water ice buried beneath the surface at various latitudes. It has hydrated minerals in the regolith, compounds that contain water molecules chemically bound to rock. Observations from orbit and from surface missions have confirmed that water exists on Mars in quantities that could, in principle, support a human presence for a very long time. In principle, the word that matters in that sentence is not water and it is not Mars. The word that matters is exists. Water existing somewhere on a planet is not the same as water being available to the people who need it. A colony does not need water somewhere in the regolith within 100 kilometers of the landing site. It needs water in a pipe. It needs water today, and tomorrow, and the day after that, in a quantity sufficient for drinking and cooking, and hygiene and agriculture, and oxygen production, and thermal regulation, and medical use, and every other thing that a functioning human settlement requires water for. A person needs roughly 2 to 3 litres of water per day just for drinking. Add cooking, hygiene, sanitation, and basic medical needs, and that rises to something closer to 50 litres per day in a resourceful, water-conscious community. Add the requirements of a hydroponic food production system. Add electrolysis for oxygen production and hydrogen fuel. Add the water used as radiation shielding inside habitat walls, and the total water that a colony needs to move and process every day becomes a serious industrial operation, not a camping trip. Here is what that operation actually looks like. If the water source is subsurface ice, which is the most practical scenario for mid-latitude landing sites, you need drilling equipment capable of reaching the ice layer, which may be several meters below the surface. Through regolith that is significantly harder than garden soil, you need heating systems to melt the ice once you reach it. You need filtration systems to remove the chemical contaminants in the meltwater. You need pumping and storage systems to move the water from the extraction point to where it is needed. You need recycling systems to capture and purify every drop of water that leaves the human body. Because on Mars, losing water means going back to extract more. And extraction is expensive in energy and equipment, life and time. Every single one of those systems requires power. Every single one requires maintenance. Every single one has failure modes. And every single one is part of a chain where failure at any link means the chain stops working. There is also a chemical problem that does not get nearly enough attention. Martian regolith contains perchlorates, compounds of chlorine and oxygen that occur naturally in the Martian environment. At several sites measured by Mars landers and rovers, perchlorate concentrations in the surface material are high enough to be a serious concern for both agriculture and direct human exposure. Water extracted from Martian sources and not properly treated is not safe to drink. The treatment processes exist, but they require infrastructure and consumables and monitoring, which adds one more system to an already long chain. Day 200. The drill team has reached the ice layer at 4.3 meters below the surface. Meltwater extraction is running. Filtration is nominal. Storage tank 1 is at 60% capacity. The recycling system is recovering 91% of grey water. 9% is being lost to evaporation and inefficiency. At current consumption rates, the reserve will last approximately 18 days if extraction stops. The drill bit is showing wear at 72% of expected service life. Replacement bits are in the cargo manifest of the supply ship, currently 7 months out. Water is not a resource until it becomes a system that runs every day, at the right rate, through equipment that wears out and breaks down and needs parts that are either already there or are not available at all. Mars may have water, but a colony does not drink possibility. It drinks supply, and supply requires something that nobody in any optimistic animation ever had to build from scratch on a planet that has never provided a drop of it willingly. Sometime around 4 billion years ago, Mars had a magnetic field. We know this because certain rocks on the Martian surface carry a fossilized magnetic signature, a record of alignment frozen into iron-bearing minerals when those rocks cooled from molten material in the presence of a global field. The field existed. It shaped charged particles away from the planet the same way Earth's field does today. It gave early Mars something resembling protection. Then the interior of Mars cooled. The liquid iron outer core that generates a magnetic field through convective motion solidified, or slowed, or both. The dynamo stopped. The field faded. And when the field faded, the solar wind, that constant stream of charged particles flowing outward from the sun at hundreds of kilometers per second, had nothing deflecting it. It hit the Martian atmosphere directly. It stripped it. Over hundreds of millions of years, particle by particle, Mars lost most of what covered it. The thin atmosphere you would choke on in seconds if you stepped outside without a suit is not the original atmosphere of Mars. It is the remnant. What you see when you look at the Martian sky is what is left after billions of years of being slowly peeled away by a star that never stopped blowing. Understanding that is important because radiation on Mars is not a single problem with a single solution. It is the downstream consequence of a planetary failure that happened billions of years ago and cannot be undone. There is no engineering fix for the absence of a global magnetic field. There is no technology on any drawing board that restores planetary magnetism to a world whose core has already cooled. The protection that Earth's field provides, deflecting and trapping the majority of incoming charged particles before they reach the surface, simply does not exist on Mars. What this means in practical terms is that the surface of Mars receives radiation from two distinct sources, and both matter in different ways. The first source is galactic cosmic rays. These are high-energy particles, primarily protons and heavier nuclei, that originate outside the solar system from supernovae and other energetic events. They arrive from all directions continuously, day and night, and they carry enough energy to penetrate significant amounts of material on Earth. The combination of the magnetic field and the atmosphere reduces the cosmic ray dose at sea level to something the human body can absorb over a lifetime without catastrophic consequences. On the surface of Mars, with no field and an atmosphere 100 times thinner than Earth's, the dose is substantially higher than anything a person living on Earth would normally encounter. The second source is solar energetic particles. These are bursts of charged particles emitted by the Sun during solar flares and coronal mass ejections. On Earth, the magnetic field absorbs or deflects most of these events. On Mars, a major solar particle event hits the surface with almost nothing blocking it. The dose from a single large event can exceed the annual occupational radiation limit for a nuclear worker on Earth. These events are unpredictable in their timing. They can last from hours to days, and there is no warning system robust enough to give a crew outside the habitat time to shelter before exposure begins. Radiation is a subject easy to overdramatize, and overdramatizing it does not help anyone think clearly about the actual problem. So here is what the science says plainly. The radiation environment on the surface of Mars will significantly increase the lifetime cancer risk of anyone who spends years there. The estimates in peer-reviewed literature vary depending on individual biology, shielding measures, activity levels, and solar behavior during the stay. But across most modeled scenarios, the career radiation limits that space agencies currently apply to astronauts would be exceeded by a Mars surface stay measured in years rather than decades. Beyond cancer, animal studies using simulated cosmic radiation have produced findings that researchers take seriously. High-energy heavy ions, the kind that make up a meaningful fraction of the galactic cosmic ray flux, cause measurable changes in neural tissue in those studies. The observed effects include impaired spatial memory and changes in cognitive flexibility. These results cannot be directly extrapolated to human beings, and the doses in some experiments differ from what a Mars colonist would receive. But the mechanism is real, the effects in animals are real, and the honest answer to what years of Mars surface radiation does to the human brain is that we do not yet fully know. Shielding helps. It does not solve the problem, but it genuinely helps. Water is excellent shielding because of its high hydrogen content. Polyethylene works well. Regolith, the Martian soil, provides meaningful protection simply through mass. A habitat built underground with several meters of regolith overhead would reduce the indoor radiation dose to something approaching acceptable levels for long-duration habitation. But shielding cannot protect people who are outside, and a Mars colony that intends to do anything beyond sitting inside a buried habitat has to send people outside. Construction, maintenance, geological survey, equipment repair, emergency response. Every hour a colonist spends on the surface in a spacesuit is an hour in an environment where the shielding is measured in millimeters of suit material and the dose is accumulating at a rate that no amount of careful planning fully neutralizes. Day 300. Radiation log shows cumulative surface dose for the crew averaging 140 millisieverts since landing. The mission commander will exceed conservative career limits within 4 years at current exposure patterns. Subsurface habitat construction is on schedule, which will reduce indoor dose significantly. But the drilling team working on the water extraction expansion has logged 40% more surface time than projected. Their individual dose curves are tracking higher than planned. There is a conversation that needs to happen about rotation schedules and what it means to ask someone to accept a biological cost that will follow them for the rest of their life in exchange for building something that might outlast them. Both. Mars does not kill with radiation. It taxes biology. Slowly. Invisibly. And every year you stay, the bill gets larger. The interest never stops accruing. In 1962, a physician and researcher named John Paul Stapp rode a rocket sled at Holloman Air Force Base in New Mexico to a speed of over 1,000 kilometers per hour, and then stopped in approximately 1 second. The deceleration force on his body reached 46 times the force of gravity. He survived. He had done it before. Many times. As part of research into the human tolerance for acceleration forces, he wore special equipment. He was secured very carefully, and he still detached both retinas, burst blood vessels in both eyes, and spent time in recovery afterward. Stapp was studying the limits of the human body under extraordinary stress, and what he found consistently was that the body is both more resilient and more fragile than intuition suggests. More resilient because it can survive things that seem incompatible with survival. More fragile because the damage from those survivable things accumulates in ways that are not always visible until much later. The human body that will go to Mars is the product of roughly 3.8 billion years of evolution on this specific planet. Every system in it, from the cardiovascular architecture that pumps blood against a one-gravity field, to the bone density that maintains structural integrity under a one-gravity load, to the vestibular system that tells you which way is down, was shaped by selection pressure for conditions that exist here and essentially nowhere else in the solar system. Mars gravity is 38% of Earth's. This is not zero gravity. Things fall. You have weight. Your cardiovascular system has to do real work, but it is not Earth gravity either. And here is the central problem. We have decades of data on what zero gravity does to the human body because we have had people living in microgravity environments going back to the early days of space stations. We have extensive data on Earth gravity because every human being who has ever lived has lived in it. What we do not have is meaningful long-term data on what 38% gravity does to a human body over years or decades. That specific environment has never existed anywhere a human being could spend significant time. We have theoretical models. We have extrapolations from the microgravity data. None of this adds up to confident knowledge about what happens to bones, muscle, the cardiovascular system, the eyes, the immune system, and the brain when a human being lives in 38% gravity for 3 years, or 10 years, or a lifetime. This is one of the most important unknowns in the entire Mars enterprise, and it receives far less attention than rocket staging or landing systems because it is harder to address with engineering. The honest answer to whether the human body can remain fully healthy in 38% gravity over the long term is that we do not know. And the way we will find out is by sending people there and measuring what happens to them. From long-duration spaceflight on the International Space Station, we know that microgravity causes bone density loss at rates of roughly 1 to 2% per month in some skeletal regions. We know that cardiovascular systems gradually restructure themselves in microgravity because the heart does not need to push blood uphill. We know that some astronauts return from extended missions with changes to vision linked to shifts in intracranial pressure, a condition that appears connected to fluid redistribution in the absence of gravity pulling fluids downward. At 38% gravity, these effects would be different in magnitude and perhaps in character. Whether they are different enough to preserve long-term health is a question no laboratory on Earth can currently answer, because the laboratory required is Mars. There is also the question of what radiation does to biology over years. Beyond the cancer risk discussed in the previous chapter, the same animal studies that showed cognitive effects from cosmic ray exposure also showed changes in immune function and inflammatory markers. The body on Mars is not just dealing with gravity, it is dealing with gravity and radiation simultaneously. And the interaction between those two stressors on human physiology has never been studied in a living human being for an extended period. Then there are the eyes. The condition called spaceflight-associated neuroocular syndrome, observed in some astronauts after long missions, involves changes to the optic nerve and the shape of the eyeball, linked to increased intracranial pressure in microgravity. In partial gravity, the fluid redistribution would be less extreme but potentially still present over years. Some Mars colonists may return, if they return, with visual changes that were not there when they left. Some may not return with fully reversible changes at all. The first group of human beings to spend years on Mars will not only be exploring a planet, They will be the first real experimental data on whether human biology can function in that environment long enough to build something permanent. Their bones and hearts and eyes and brains will answer questions that no simulation and no Earth-based study can answer. And those answers will come at a cost that only they will pay, carried in their bodies for the rest of their lives, regardless of what the data shows. The body was built for here, for this gravity, this atmosphere, this radiation environment, this specific set of conditions that have existed on this planet for the entirety of the time our species has existed. Mars did not factor into that design. The body carries no preparation for it, no adaptation shaped by millions of years of selection pressure for that environment, because no ancestor of ours ever stood on Martian ground and survived long enough to pass on whatever helped them do it. The first long-term Martians will not only explore Mars, they will let Mars explore the limits of a human body that was never built for it. And the results of that exploration will not be known until someone has already spent years paying for the answer. On the 28th of May, 2018, a dust storm began forming over the Perseverance Valley region of Mars. Within 2 weeks, it had grown to cover an area larger than North America. Within a month, it had become a planet-encircling event. A suspended veil of fine particles so dense that orbital cameras could barely image the surface beneath it. On the 4th of June, the Opportunity rover, which had been operating on the Martian surface for more than 14 years, sent its last transmission. The storm had reduced available solar power to a fraction of what the rover needed to keep its batteries charged. Opportunity went into a protective low-power mode and waited for the storm to pass and the sky to clear. The sky cleared. Opportunity did not wake up. NASA engineers spent months sending recovery commands. They tried different frequencies. They adjusted timing. They hoped the batteries might have held enough charge to restart the systems. Nothing worked. On the 13th of February, 2019, after 45 recovery attempts and a silence lasting more than 8 months, NASA declared the mission over. Opportunity was not destroyed by the storm. It was not buried or overturned or damaged by wind. It simply ran out of power because dust blocked its solar panels. And without power, the heaters that kept its electronics from freezing in the Martian night could not run, and the cold killed the batteries. And without batteries, nothing came back. That was a rover. It needed only one thing, and dust took that one thing away in a matter of weeks. Now, think about a human colony running on solar power when that storm arrives. Think about what happens in the first week. When the sky dims and power generation drops, and the systems that run on electricity begin drawing from reserves not designed to last through a planet-encircling event. Think about the second week, when decisions have to be made about which systems get power and which go offline. Think about the third week, when greenhouse lighting dims and water extraction slows, and everyone on the base has a very clear and very uncomfortable understanding of how thin the margin actually is. But the storm scenario, dramatic as it is not the most dangerous thing about Mars dust. The storm is visible. It is dramatic. It forces a response. The more dangerous problem is what happens on every single ordinary day. Without drama, without emergency alerts, without any moment of crisis that demands immediate action, Mars dust is not like household dust. It is the product of billions of years of geological grinding in an environment with no liquid water to bind particles into larger aggregates, and no biological processes to break down and recycle surface materials. The result is particles that can be measured in microns, fine enough to remain suspended in the thin Martian atmosphere for months, electrostatically charged in ways that make them cling to surfaces with unusual tenacity, and chemically active in ways that matter for anything biological or mechanical they come into contact with. Picture a colonist returning from a surface excursion. The airlock cycles. The outer door closes. The inner door is still sealed. In the airlock, between those two doors, the colonist stands in a suit, covered from helmet to boot in a layer of fine reddish-brown dust. They go through a decontamination procedure, brushing and vacuuming as much of the dust away as possible before entering the habitat. They remove the soot in a carefully managed process designed to minimize the amount of dust that enters the living area. Some dust enters the living area. It always does. The particles are too small, too clingy, and too numerous to be completely excluded from any environment that human beings move in and out of regularly. Over days and weeks and months, dust accumulates in places it was never supposed to reach, in the hinges of equipment housings, in the gap between a cable and the bulkhead fitting it passes through, in the groove of the airlock door seal that is supposed to create an airtight barrier between inside and outside. That seal is worth thinking about carefully. An airlock door seal is conceptually simple, a piece of flexible material that compresses against a mating surface and prevents gas from passing through the gap. On Earth, these seals work reliably for years because the environments they operate in are relatively benign. On Mars, the seal is exposed to dust every time the airlock cycles. Each cycle grinds a few more microns of dust into the seal material. Each cycle causes a tiny bit more wear. The seal does not fail dramatically. It degrades, gradually, invisibly, until one day, the pressure sensor in the airlock records a reading 3% outside the expected range. And someone has to decide whether that is sensor drift or the beginning of a leak. Solar panels lose efficiency as dust accumulates on their surfaces. Optical instruments develop degraded performance. Mechanical joints experience increased friction and wear. Filters clog faster than their Earth-equivalent testing predicted. Thermal surfaces that need to radiate heat efficiently become insulated by dust deposits. And this is happening simultaneously, to all of the equipment, all of the time, at a rate that is difficult to predict, precisely because no one has run a Mars colony for 10 years and measured the actual degradation curves. The perchlorate compounds found in Martian regolith add a biological dimension to the problem. At several sites measured by Mars landers and rovers, concentrations in the surface material are high enough to be a concern for human health with chronic exposure. Dust that enters the habitat carries regolith material. Dust that is inhaled carries whatever is in it. The long-term respiratory effects of Mars dust exposure have not been studied in humans because no human has ever been exposed to it. Year 2. The maintenance log for the primary airlock seal shows replacement intervals have shortened from the design schedule by 31%. Bearing wear in the spacesuit joint assemblies is tracking ahead of projections. The optical sensor on the water extraction unit outside has been manually cleaned 4 times this month. The dust filter in the greenhouse ventilation system was replaced 2 weeks ahead of its projected service life. None of these items are emergencies. Each one, individually, is a minor maintenance event. Together, they're a picture of a colony being slowly eaten by its environment, 1 micron at a time, whose survival depends entirely on whether the supply of replacement parts stays ahead of the demand. Mars dust does not need to destroy the colony in one storm. It only needs to enter everything the colony depends on and wait for the cumulative damage to do the work. When the film version of The Martian came out in 2015, one scene became the thing people remembered and quoted and used as shorthand for what Mars survival might actually look like. Mark Watney, stranded alone on Mars, calculates that he can grow enough food to survive until rescue by farming in the habitat. He fertilizes the Martian soil with human waste. He plants potatoes. They grow. He eats them. The scene works as cinema because it takes something terrifying and transforms it into something that feels manageable. Here is a problem. Here is a clever solution. Here is a man refusing to die by applying basic agricultural science to a hostile environment. Audiences responded to it because it captures something true about human ingenuity and something emotionally compelling about the refusal to give up. It skips several facts that matter considerably. The most immediately relevant is the chemical problem. Martian regolith contains oxidizing compounds at concentrations that make it incompatible with direct food production without significant treatment. At several sites measured by Mars missions, perchlorate concentrations in the surface material are high enough to be a serious concern for human health and for agriculture. Growing plants in raw Martian soil and then eating what those plants produce is not a survival strategy. It is a slower version of poisoning yourself. Adding human biological waste as fertilizer would introduce organic material, but it would not neutralize the chemical problems already present in the regolith. But this is almost the minor point, because the perchlorate issue has solutions. Perchlorates can be removed through a combination of water washing and biological treatment using perchlorate-reducing microorganisms. The chemistry is understood. The methods exist. They require infrastructure and time and energy and water, all of which are scarce on Mars. But the path is at least visible. The deeper problem is harder to treat because it is not a contamination problem. It is an absence problem. Reach down and grab a handful of soil from a garden, not potting mix from a bag. Actual dirt from the ground outside. What you are holding is not a substrate. It is not a growing medium in the way that a sponge soaked with nutrient solution is a growing medium. What you are holding is one of the most complex biological communities on Earth. A single gram of healthy agricultural soil contains somewhere between 100 million and 1 billion bacterial cells from thousands of different species. It contains fungi, including the mycorrhizal species that form symbiotic relationships with plant roots and extend their effective reach for nutrients by orders of magnitude. It contains protozoa that feed on bacteria and release nutrients in forms plants can absorb. It contains nematodes and microarthropods and an entire food web of organisms whose collective activity breaks down organic matter, cycles nutrients, maintains soil structure, suppresses plant pathogens, and performs hundreds of other functions that a plant growing in that soil depends on completely. This community took billions of years to evolve. It is maintained by continuous inputs of organic matter from plants and animals and decomposers, and it is what makes food production on Earth possible at the scale that feeds 8 billion people. Martian regolith contains none of it, not because it was present and then destroyed, because it was never there. Mars has no biology. Mars has never had biology of the kind that builds soil. The surface material of Mars is a geological product, mineral and chemical, shaped by volcanic activity and impact, cratering, and atmospheric chemistry, but never by life. It is not depleted soil. It is not poor soil. It is not soil at all in any sense that a farmer or a gardener would recognize. It is ground-up rock with a chemical signature that reflects a planetary history entirely devoid of living things. To grow food in it, you do not improve it. You replace it. The practical approach to food production on Mars is controlled environment agriculture, hydroponic or aeroponic systems, where plants grow with their roots in nutrient solutions or carefully managed artificial substrates, shielded from the Martian atmosphere, lit by artificial lighting, heated against temperatures that would kill most food crops within hours of exposure. These systems work. Hydroponic farming is well established on Earth and can produce high yields in small spaces with efficient water use. But hydroponic systems require nutrients that have to come from somewhere. Either you bring them from Earth at enormous cost, or you produce them from local resources, which requires industrial chemistry infrastructure that adds more layers to an already complex system. They require energy, substantial amounts of it. To run lighting and climate control and pumps and monitoring systems, they require water, which we have already discussed. And they are biological systems, which means they are vulnerable to pests and pathogens in ways that a power conduit or a water pipe is not. A plant disease that spreads through a hydroponic system can destroy a crop in days. On Earth, a farm that loses a crop has options. Buy from a neighbour, order from a distributor, plant a different variety. En masse. A colony that loses a significant portion of its food production has whatever reserves it stored before the problem started, whatever it can ration from remaining productive systems, and a supply ship that is either already in transit or will not launch for another 18 months. The caloric math is not generous. A working adult, under normal conditions, needs roughly 2,000 to 2,500 calories per day. Under the physical demands of construction work and equipment maintenance in heavy suits, that number goes up. Every square meter of growing area is a pressurized, heated, powered, watered, and maintained system that adds to the total complexity the colony has to sustain. And the nutritional completeness of a Mars diet depends on the diversity of what can actually be grown in artificial conditions, supplemented by whatever vitamins and minerals can be produced locally or shipped from Earth. The Martian image of a person growing potatoes in Martian soil and eating them and surviving is one of the most appealing images in the popular imagination of Mars colonization. It is appealing because it suggests that Mars, for all its hostility, will at some level cooperate, that the ground will accept a seed, that life will find a way. The reality is that Mars will not cooperate. The ground will not accept a seed without years of careful preparation and enormous ongoing inputs of energy and chemistry and biological complexity that Mars does not provide and never has. The first Martian farm will not be a field under a natural sky. It will be a life support machine with leaves, a controlled environment that has to maintain precise conditions without interruption, sustained by power and water and nutrients that all have to come from somewhere, under light that has to be generated because the real light is too variable and too often blocked by a sky full of suspended particles, and it will fail the moment anyone mistakes it for nature. On the 9th of August, 2003, a software bug in a grid management system in Ohio triggered a cascade that knocked out power to 55 million people across 8 states and 1 Canadian province. It happened in about 9 seconds. Traffic lights went dark. Subway systems stopped mid-tunnel. Hospitals switched to emergency generators. Air conditioners went off during a summer heat wave. Most people were without power for between 1 and 4 days. Nobody inside the affected area suffocated. Nobody froze to death in their home. The water in the pipes continued to flow, at least for a while. Food in refrigerators stayed cold for approximately 4 hours before people started worrying about it. People opened windows. They lit candles. They complained and sweated, and some of them died. Mostly elderly people vulnerable to the heat. And it was genuinely bad. But the overwhelming majority of 55 million people endured it as a serious inconvenience and went back to normal when the power returned. Now, remove the option of opening a window. Remove the outside air that would come through the window, which on Mars is 95% carbon dioxide at a pressure that would kill you. Remove the water in the pipes, which on Mars requires powered extraction and pumping at every stage from the ice to the faucet. Remove the food that was in the refrigerator, which on Mars is growing under artificial lighting in a hydroponic system that requires powered pumps and climate control to keep the plants alive. Remove the 4 walls of the building, which on Mars are a pressurized habitat whose internal atmosphere is maintained by powered systems running continuously. Remove the hospital down the street, which on Mars is a medical bay inside that same pressurized habitat, running diagnostic equipment and sterilization systems and climate control on the same power grid that just went dark. Remove the generators that the hospital switched to, because on Mars the backup power system has a finite capacity designed to cover a specific failure duration, and if the primary system does not come back within that window, the backup runs down too. What you have now is not an inconvenience. What you have is a countdown. The power problem on Mars is not about whether electricity is convenient or comfortable or conducive to modern life. Every single life support system, every single food production system, every single water extraction and purification system, every single communication system, every single medical system, and every single environmental control system in a Mars colony runs on electricity. Not some of them, all of them. There is no analog fallback. There is no manual alternative that keeps people alive when the power goes. There is no opening a window and catching a breeze. Power on Mars is not infrastructure the way roads and internet cables are infrastructure. Power on Mars is the prerequisite for everything that keeps biological organisms alive in an environment that has no interest in doing that job itself. So where does it come from? Solar is the obvious first answer. Mars gets sunlight. Solar panels convert sunlight to electricity. The technology is mature and well understood and increasingly efficient. The case seems straightforward until you look at the numbers. Mars receives roughly 43% of the solar energy per square meter that Earth does, because it is farther from the Sun. That alone requires a significantly larger panel array to produce equivalent power. Then there is dust. Dust settles on panels continuously and reduces output. The Opportunity rover experienced this and sometimes benefited from wind events that cleared its panels. A colony cannot rely on wind events. It has to clean its panels regularly, which requires people and time and equipment in a context where all three are expensive. And then there are the storms. A planet-encircling dust storm, the kind that occurs every few Martian years, can reduce solar panel output to near zero for weeks. For a colony running primarily on solar power, a major dust storm is not a weather event. It is a threat with a multi-week timeline arriving on a schedule that nobody can precisely predict. Nuclear fission is the stronger answer. A compact fission reactor offers power independent of sunlight, unaffected by dust, consistent regardless of time of day or season. NASA's Kilo Power project demonstrated a small-scale version of this technology in 2018, and the results were promising. Nuclear power addresses almost every weakness that solar has on Mars. It also brings its own complications. A fission reactor is complex equipment that requires careful siting away from inhabited areas because of its radiation output. It requires cooling systems that function in an environment with almost no atmospheric pressure to help with heat rejection. It requires enriched fissile material produced on Earth and launched into space, which carries regulatory complexity and political sensitivity that has historically added years to timelines. And it requires maintenance, because reactors have components that wear and degrade and need attention by people who know exactly what they are doing. The realistic answer for a serious colony is probably both. Solar for lower power baseline operations when conditions are good. Nuclear for heavy load and storms and the long Martian nights and the seasons when Mars is furthest from the Sun. A hybrid system with multiple generation sources and storage, and a management system that handles the allocation of power to competing demands under varying conditions. That system has to work every day, because the cascade that follows when it does not is not an inconvenience. Power falls. Heating falls. The temperature in the habitat begins dropping toward the ambient outside temperature, which on a Martian winter night can approach negative 100 degrees Celsius. Water extraction stops. Air processing slows. Carbon dioxide levels begin to rise. The greenhouse lighting dims and the plants begin to die. Medical equipment stays on backup power, but the reserve is finite. Communication systems remain up because they are prioritized, but there is less and less to report that anyone wants to hear. Year 5. The solar array is producing 68% of rated capacity after cumulative dust degradation and 2 panel replacements. The nuclear reactor is operating nominally and providing baseline power. The system is in balance. Then a microcrack develops in the primary coolant loop of the reactor, discovered during a routine inspection. The reactor has to be shut down for repair. The process is estimated at 4 days. For 4 days, the colony runs on solar and battery alone. Day 1 of the repair. Solar input is good. Battery reserves are healthy. All systems nominal. Day 2. A partial dust event reduces solar output by 30%. Battery draw increases. Greenhouse lighting is reduced to minimum viable levels. Water extraction is throttled back. Day 3. Dust continues. Battery reserves are at 52%. A decision is made to shut down non-essential electrical loads. The list of non-essential loads is very short because almost everything is essential. Day 4. Battery reserves are at 31%. The repair team is working through the night. The parts fit. The reactor restarts at 14 minutes past midnight. In the morning, the colony director writes in the log that the incident demonstrated the value of the hybrid power architecture and identified several areas for reserve improvement. What she does not write, because it does not need to be written, is that she spent most of day 3 running the numbers over and over and arriving at the same conclusion every time. 31% was close enough to the edge that she could see the edge clearly. On Mars, a power outage is not darkness. It is the first second of every other system becoming a question. Imagine you are the chief medical officer of a Mars colony. You have been awake for 19 hours because yesterday the water extraction lead developed a fever, and you spent most of the afternoon ruling out the serious possibilities and concluding it was probably viral. Rest and fluids. Watch for complications. It is 2 a.m. Colony time. When the knock comes on your door, one of the construction crew, he is holding his right side, just below the rib cage, walking slightly bent. He says it started a few hours ago. Thought it would pass. It has not passed. You bring him to the medical bay. You run through the possibilities. The location and character of the pain puts appendicitis at the top of your list. But kidney stone fits too. And so does muscle strain from the suit work. And so does a dozen other things, with varying degrees of urgency. On Earth, this is a 30-minute emergency room visit that ends with an ultrasound and a clear diagnosis. You have a portable ultrasound unit. You have used it many times. You are reasonably skilled with it, but you are not a radiologist. And the image you are looking at is ambiguous in the way that images are when the person reading them is working at the edge of their training. You send the images to Earth with your clinical notes. You ask for a second opinion. The response will arrive in somewhere between 12 and 40 minutes depending on where the planets are in their orbits today. You already knew that when you sent the message. You also know that the response, when it comes, will be based on the information you provided, interpreted by someone who cannot examine the patient, cannot ask follow-up questions in real time, and cannot be present for what happens next. If this is appendicitis and you wait, the appendix may perforate. Peritonitis in a Mars colony with limited antibiotic reserves and no surgical backup is a situation you do not want to manage. If this is not appendicitis and you operate, you have exposed a person to the risks of surgery performed in a facility that is not a hospital, by a surgeon who has the training but not the volume of a working emergency surgeon, using instruments and anesthetics from a supply that cannot be quickly replenished. This is not a hypothetical designed to be dramatic. This is a real decision structure that the medical officer of any serious Mars colony would face with some regularity. Across a range of conditions from the straightforward to the life-threatening, it is the structure of medicine without a safety net, and it looks very different from medicine with one. On Earth, the safety net for medical care is so deeply woven into everyday life that most people are not aware of its existence until it is needed. A city of 100,000 people might have 3 hospitals, dozens of clinics, hundreds of physicians, specialists in every significant field, pharmacies stocked with thousands of medications, blood banks with multiple types on hand, and a paramedic system that can put trained personnel on scene in less than 10 minutes. Behind all of that is a supply chain delivering pharmaceutical products from factories around the world, medical device manufacturers who can ship replacement parts within days, and medical schools training thousands of new physicians every year. A Mars colony has none of that behind it. What it has is what it brought. Pharmaceuticals degrade. Most medications have shelf lives measured in months to a few years under proper storage conditions. A colony needs not just the drugs its members currently require, but a reserve sufficient to cover emergencies that cannot be predicted. Managing that reserve, ensuring critical medications are always within their effective period, replacing them before they expire, requires a continuous resupply relationship with Earth operating on a timeline measured in years. A medication expiring in 8 months needs to be on an Earth launch that has already happened, or a replacement needs to be on the next available window. Blood is perishable. Whole blood has a shelf life of roughly 42 days under refrigeration. A surgical emergency requiring transfusion in a colony of 20 people is a serious problem, not because blood does not exist among the colonists, but because the right type has to exist. In sufficient quantity, fresh enough to use, at the moment it is needed. Dental care is almost never discussed in Mars colonization literature, which is striking because dental problems are among the most common medical issues in any population. An untreated dental abscess can progress to a systemic infection with serious consequences, The dentist on a Mars colony needs to handle the full range of dental emergencies with whatever equipment and materials are on hand. Mental health presents its own specific challenges. The psychological stresses of confinement, isolation, radiation exposure, constant operational risk, and separation from everyone a person has ever loved will affect some proportion of the colony population in ways that require clinical intervention. The clinician providing that mental health care is also a member of the same community experiencing the same stresses as everyone else. Some people on Mars may die from conditions that would have had far better survival odds on Earth. Not from heroic accidents in dramatic circumstances, from infections that found the right antibiotic was out of stock, from complications in emergencies where the specialist was not there. That is a truth about Mars colonization that the people planning it understand and rarely state plainly in public. It is not a failure of planning or a consequence of insufficient technology. It is the baseline condition of medicine practiced at the edge of the human world, where the safety net that everyone on Earth takes for granted simply does not exist. And every decision carries the full weight of its own consequences. A Mars colony does not need a doctor. It needs a hospital small enough to fit inside a habitat and deep enough to replace everything Earth sends in an ambulance. And it needs that hospital to never run out of anything critical, and for the person running it to never get sick themselves, and for every serious case to be survivable with the tools available. None of those conditions can be guaranteed. That is the honest reality of medicine without a safety net. In the winter of 1913, a Norwegian explorer named Jørgen Stubberud spent the dark months at a small base on the Ross Ice Shelf with 2 other men as part of Roald Amundsen's South Pole Expedition support team. The polar night lasted 4 months. The temperature outside was lethal. They could not leave. They had each other, their work, their provisions, and the walls of a wooden hut. One of them stopped talking to the others for 6 weeks. Not because of a dramatic argument, not because of a specific incident that could be identified and resolved. He simply withdrew, ate his meals in silence, performed his duties, responded to direct questions with minimal words. The other 2 men continued their routines around him, respecting the withdrawal while privately measuring its depth and duration, aware that in their situation there was no intervention available beyond patience and the slow passage of time. He eventually came back. By the time the darkness lifted and the work resumed, the dynamic had mostly normalized. Nobody wrote much about it afterward. It was filed under the category of things that happen when people are confined together in extreme conditions for a very long time. And then it was left there. That base had one thing a Mars colony does not have. When the darkness ended, the door could open. The outside world, however frozen and inhospitable, was an outside. The walls were not the entirety of existence, and the men inside knew the condition was temporary in a way that was calendar certain. They knew when it would end. On Mars, the walls are the world, and nobody knows exactly when it ends, because ending it requires a launch window and a transit, and a series of decisions made by people hundreds of millions of kilometers away, who have their own priorities and their own timelines that do not necessarily align with the moment. When someone inside the habitat has used up their capacity to keep doing this. The psychological challenge of long-duration Mars habitation is one of the most seriously studied and least publicly discussed aspects of the entire enterprise. NASA and other space agencies have invested considerable resources in understanding what happens to human minds in confined, isolated, high-stakes environments over extended periods. The picture that emerges is not catastrophic in its broad strokes. Human beings are remarkably resilient. People have survived and functioned under conditions that seem, from a comfortable remove, to be incompatible with psychological health. But adaptation is not the same as unaffected, and the specific combination of factors that a Mars colony presents is one that has never been tested at full scale, for full duration, with full consequences. Start with the communication delay. The distance between Earth and Mars varies between roughly 56 million and 400 million kilometers, depending on where both planets are in their orbits. At the speed of light, A signal takes between 3 and 22 minutes to cross that distance one way. A conversation in the familiar sense. Two people exchanging words in something approaching real time is not possible. What is possible is an exchange of messages, more like letters than phone calls, with a minimum round-trip time of 6 minutes on the best day and 44 minutes on the worst. For a person who has just received bad news from home, or who is frightened and needs reassurance, or who has had a serious conflict with a crewmate and needs the perspective of someone outside the situation, the delay is not merely a technical inconvenience. It is a restructuring of the emotional landscape. The people who love you and want to help you are present only as words on a screen that arrive in batches and cannot respond to what you said 20 minutes ago because they have not received it yet. And if there is an emergency, a medical crisis or a psychological breakdown, the delay means that Earth cannot help in real time. Ground control can advise. Ground control can offer expertise and presence in whatever form. A text message with a 40-minute round trip can offer. But the decision, the action, the management of whatever is happening right now, falls entirely on the people in the room. Always. Now think about what that does to a group of 6 people over years. Every conflict stays in the room. Every grievance accumulates without the social pressure release valves that normal human communities take for granted. The ability to walk away, to spend time with different people, to change your environment, to get physical distance from the person whose specific way of doing something has been irritating you for the past 4 months. En masse. There is no walking away. There is a habitat. There are 6 people. The habitat is the entire world. The Mars 500 study, conducted in Moscow between 2010 and 2011, placed 6 volunteers in a sealed facility, simulating a Mars mission for 520 days. They could not leave. Outside contact was managed to simulate communication delays. Researchers monitored their sleep, physical activity, and social dynamics throughout. What the study found was not a story of breakdown. Most participants completed the isolation in reasonable psychological health and reported the experience as meaningful. But the study found subtler patterns that matter for planning a real mission. Over time, activity levels declined. Sleep timing drifted. Some participants became increasingly sedentary and socially withdrawn in ways the monitoring systems could track, but the participants themselves may not have fully recognized. Group dynamics shifted in ways that were gradual and not always visible to the people inside them. And Mars 500 had an exit. Everyone inside knew with calendar certainty that the door would open on a specific date. The psychological weight of a real Mars mission, where the duration is genuinely uncertain and the return depends on systems and decisions and circumstances the crew cannot fully control, is different from a simulation that has a guaranteed end date. There is one more dimension of the psychological challenge that almost never appears in mission planning documents. It is grief. People on Mars will lose people on Earth. Parents will die. Relationships will end. Friends will have births and deaths and milestones that pass without the Mars colonist present. The person who left Earth for Mars left behind everyone they knew. And the distance is not just spatial. It is the distance of time passing on both sides of the gap. The Earth that they left, and the Earth that exists now diverging from each other with every month that passes. There is no way to fully prepare for that. There is no training simulation that gives someone the experience of sitting in a habitat on another planet, reading a message that their father died 6 hours ago and the signal just arrived, knowing that the funeral is already over and everyone who loved him gathered without them, and there is nothing to do and nowhere to go, and the habitat is still the same habitat. It was this morning, and tomorrow it will be the same habitat. Again, on Earth. Grief has geography. You can go somewhere. You can be held. You can stand in a room full of people who are also sad. En masse. Grief has only the room it started in, and 6 people who are carrying their own versions of the same weight, and a fan humming in the wall that does not know or care what just happened. On Earth, you can leave the room. On Mars, the room is the world. And the world is 6 people who cannot afford to stop trusting each other, even when trust is the hardest thing any of them has left. On the 18th of April, 1876, a surveying team working in the Nevada desert ran out of axle grease. This is not a story that made it into the history books, because the surveying team solved the problem by improvising a lubricant from rendered animal fat and kept moving, and their survey was completed on schedule, and nothing notable followed from the incident, except a notation in the expedition log that read, essentially, ran out of axle grease, used animal fat. Problem solved. Continued. The reason this worked out the way it did is not because the people involved were especially clever or lucky. It is because the environment they were operating in, as harsh as the Nevada desert can be, was still an Earth environment. It had animals. It had organic materials. It had the accumulated knowledge of centuries of human beings solving exactly this kind of problem in exactly this kind of place. The nearest town with a hardware supply was measured in days, not years, and the cost of the delay, if the improvised solution had failed, was measured in inconvenience, not in the lives of everyone on the expedition. En masse. There is no animal fat. There is no town 3 days away. There is no improvised solution that uses materials the environment provides, because the environment provides nothing that human technology can use without extensive processing, and the cost of the delay, when the delay is long enough and the component critical enough, is not measured in inconvenience. This is the spare part problem, and it is in some ways the most honest summary of the entire colonization challenge, because it is not about any single dramatic failure. It is about the ordinary, inevitable, relentless degradation of mechanical and electronic systems operating in a hostile environment without access to the supply chains those systems were designed to rely on. Every machine breaks. This is not a design flaw or a failure of engineering. It is physics. Materials fatigue under cyclic stress. Seals degrade under repeated compression and decompression. Bearings wear as the surfaces in contact with each other exchange microscopic amounts of material with every rotation. Electronics develop resistance, degradation, and capacitor aging over thousands of hours of operation. Software accumulates edge cases that turn into bugs. Sensors drift from their calibrated values. Lubricants break down. Filters clog. Pumps cavitate. None of these failures are catastrophic in isolation. Under normal circumstances, on a planet with a supply chain, on Earth, the response follows a well-worn path. You diagnose the problem. You identify the failed component. You order the replacement from a supplier who has it in stock. It arrives. You install it. The system returns to service. The entire global economy is structured around this model. The logistics networks, the warehousing systems, the manufacturing supply chains. All of it exists to make the process of replacing broken components fast and reliable enough that the systems, depending on those components, can keep running. En masse. None of that exists. What exists is what was brought. Think carefully about what that means for a colony that intends to operate for years or decades. Every component in every system has a finite service life. The air recycling system has filters that need replacement. The water extraction unit has pumps and drill bits and filtration membranes that wear out. The power distribution system has connectors and regulators that fail over time. The medical bay has diagnostic equipment with consumable elements. The spacesuits have seals and joints and pressure bladders that degrade with every excursion. Every single one of those replacement items has to be either already on Mars somewhere in the colony's inventory, on a spacecraft currently in transit, or on a spacecraft that will launch within the next available window, which comes every 26 months. Year 5. The maintenance log records that the primary bearing assembly in the ventilation rotor of Habitat Module 3 is showing vibration characteristics outside the normal range. The bearing has not failed. It is showing the early signature of a failure that will happen, based on the degradation curve, in somewhere between 60 and 180 days. The replacement bearing for this specific assembly is a precision component that the colony's current fabrication capabilities cannot match. It is listed in the colony's parts inventory as a quantity of 2. Both are accounted for in the storage manifest. One problem. The storage manifest was last physically audited 14 months ago. The colony has grown since then. New modules added. Storage areas reorganized. Inventory moved during the expansion. A physical search for the bearing location shows the storage container listed in the manifest. The container is there. The container is empty. Someone moved the bearings. Nobody recorded where they moved them to. The bearing is somewhere on Mars. Probably. It might have been used in a repair that was not logged correctly. It might be in any of several hundred storage containers across multiple modules. The search takes 3 days. The bearing is found in a container labeled Miscellaneous Hardware, adjacent to the fabrication bay. Both units are there. The repair is completed. The ventilation system returns to normal operation. But during those 3 days, while the search was ongoing, the ventilation in Module 3 ran on reduced capacity. The carbon dioxide concentration in that module climbed slowly but measurably. The 4 people working in that module breathed slightly elevated carbon dioxide for 72 hours. The effects are subtle. A mild increase in respiratory rate. A barely perceptible decrease in cognitive performance. Nothing that registers as a medical event. But it happened. And it happened because a bearing could not be located in an inventory system that was imperfect. Now multiply that story by every mechanical and electronic system in the colony. Multiply it by 5 years, 10 years, 20 years. Multiply it by the accumulated effect of every small imperfection in documentation, every informal repair that bypassed the proper logging procedure, every component installed in a hurry during an emergency that was not recorded correctly afterward. 3-dimensional printing has been proposed as a partial solution to the spare parts problem, and it is a genuine partial solution. A colony with a capable fabrication system and the raw materials to feed it can manufacture a meaningful range of replacement components without waiting for a resupply mission. This is real and represents meaningful progress toward the kind of self-sufficiency that a colony would eventually need. But printing a structural bracket or a simple housing is different from printing a precision bearing that will carry a dynamic load at the tolerances required for reliable operation in a life-critical system. That requires not just a capable printer but a materials supply chain that provides the right feedstock. A quality assurance process that verifies the printed part meets the required specifications, and the knowledge to know when a printed replacement is good enough and when it is not. That knowledge is institutional. It exists inside the collective expertise of manufacturing engineers who have spent careers understanding the failure modes of specific components in specific applications. It exists in testing protocols developed over decades. It exists in the memory of every incident where a part that looked right turned out not to be right, in ways that only became apparent under load or over time. Carrying that knowledge to Mars means not just bringing the printing equipment, but bringing the people with the expertise to use it correctly, training more people to replace them when they are no longer available, and building a system for capturing and transmitting that expertise to the next generation born on Mars who never had the training pipeline of Earth to learn from. A colony is not alive because it has machines. It is alive because it can repair those machines, replace those machines, and eventually reproduce the knowledge that makes those machines possible. That is not engineering. That is civilization. And civilization, in this context, is not an abstraction. It is a bearing, found after 3 days of searching, installed by someone who knew what they were doing, in a system that then kept running, and the next time, and the time after that, for as long as the colony intends to exist. 6 months into the mission, the water recycling system is running at 94% efficiency. The shortfall, 6% of processed water being lost rather than recovered, is within design tolerance. But the greenhouse team has run the numbers, and the numbers are not comfortable. At the current rate of loss, the colony will fall below minimum agricultural water requirements before the end of the Martian winter season. when solar power is reduced and the colony will be drawing most heavily on food reserves. Their solution is a 12% reduction in personal water consumption across the colony, covering hygiene, cooking, and individual use. The medical officer objects. The evidence base for hydration in people performing heavy physical labor under elevated radiation and partial gravity supports current consumption levels. A 12% reduction is not a minor inconvenience. It is a medical risk that compounds the physiological stresses the crew is already managing. The engineering team has a third position. They believe the recycling system's efficiency can be improved by a maintenance procedure not yet attempted on Mars. One that would take 2 people offline from their regular duties for 5 days and requires consumables from the limited repair inventory. The procedure might bring efficiency to 97%. It might introduce failure modes that the maintenance team has not fully characterized. Who decides? Not who is technically in charge. That question has an assigned answer. The deeper question is whose decision this actually is. What happens when the formally designated decision-maker chooses something that a significant portion of the community believes is wrong? And what enforcement mechanisms exist on a world where the person with authority over water allocation also has authority over the air that everyone in the room is breathing? That question, playing out in a habitat smaller than most suburban homes, between 6 people who cannot walk away from each other and cannot appeal to any institution that can physically arrive to help, is the governance problem of Mars colonization. And it begins not with constitutions or flags or formal declarations, but with moments exactly like this one, where the stakes are physical and immediate, and the framework for resolving disagreement has not yet been built. The Outer Space Treaty of 1967 establishes broad principles for the peaceful use of outer space and the responsibility of states for activities carried out by their nationals. It is a landmark document that has served an important purpose for more than half a century. What it does not provide is an operating system for the practical governance of a private settlement, including questions of labor relations, resource allocation, punishment for violations of colony rules, emergency authority, and the rights of people who were not born on Earth and did not sign an employment contract as adults, but are nonetheless living under whatever governance structure exists. The treaty was designed for an era when spaceflight was a government activity, and the relevant actors were nation-states with established legal personalities. It was not designed for a scenario in which a private company has transported 100 people to another planet. Those people are entirely dependent on the company's infrastructure for survival. The company's investors expect a financial return, and some of those people have children who are Mars residents by circumstance rather than by choice. History offers instructive parallels, none of them entirely comfortable. Jamestown, the first permanent English settlement in North America, was financed by the Virginia Company of London. The company held the charter. The company had specific expectations about what the settlers would produce, and specific authority over the governance of the enterprise. The settlers had specific needs that the company's structure was not designed to meet, and specific grievances that accumulated through the first terrible years of starvation and disease and conflict, with a governing structure managed from thousands of kilometers away by people who had never seen the place they were governing. Within a year, the original governing council had collapsed. A man named John Smith had assumed effective authority through practical competence rather than through the formal structure the company had designed. The colony nearly failed completely, and survived only through the arrival of supply ships at the last possible moment. What happened in Jamestown is not a worst-case cautionary tale. It is a fairly typical outcome for a colony whose governance structure was designed by an institution 4,000 kilometers away for purposes that did not fully align with the survival priorities of the people on the ground. On Mars, the institution will not be 4,000 kilometers away. It will be anywhere from 56 million to 400 million kilometers away. The communication delay will ensure that every instruction arriving from Earth addresses a situation that has already resolved itself one way or another before the instruction arrives. The people on Mars will, by physical necessity, govern themselves in real time. The question is not whether they will do so. The question is what framework they will use and who built it and whether it was built for their actual situation or for a situation that existed only in a planning document written on another planet. There is a harder question underneath all of this, one that the planning documents avoid because it does not have a clean answer. On Mars, political authority will ultimately rest on control of life support. The person or group that controls the oxygen production system controls the most fundamental resource in the colony. The person or group that controls water allocation controls the second most fundamental resource. In a community small enough that everyone knows everyone, where the social contract is enforced not by police and courts, but by the daily reality of mutual dependence on shared systems. Authority and survival are not separate questions. They are the same question asked from different angles. Every colony in history has eventually confronted the tension between the authority of the institution that created it and the self-determination of the people who live in it. That tension has never been resolved peacefully, when the stakes were high enough and the distance was large enough, and the interests of the institution and the community diverged far enough. Mars will not be the first place this happens. It will be the place where the stakes are higher and the distance is greater and the dependence is more absolute than anywhere this has happened before. On Mars. Politics will not begin with flags or constitutions or formal declarations of anything. It will begin the first time two people disagree about who gets to decide when there is not enough of something for everyone's plan, and the answer to that question, and the process by which it is reached, will determine whether the colony becomes a community or something considerably less comfortable to describe. In the summer of 1848, a carpenter named James Marshall found gold in the tail race of a sawmill he was building on the American River in California. Within 2 years, roughly 300,000 people had arrived from across the United States and around the world, drawn by a reason to go that anyone could calculate on the back of an envelope. The risk was real, the hardship was serious, the distance was significant, and people went anyway, by the hundreds of thousands, because the logic was clear enough to act on independently without waiting for anyone to organize them. California did not stay a mining camp. The infrastructure built to support the miners became the foundation of an agricultural economy, then an industrial economy, then a technological economy that, roughly 170 years later, produces more economic output than most countries. The reason that got the process started was not the reason that sustained it. It was just the reason that got people there in sufficient numbers to build something that could eventually sustain itself. Now look at Antarctica. The continent has been continuously occupied by scientific research stations since the International Geophysical Year of 1957 and 1958. Multiple nations have maintained permanent presences there ever since. People live there, work there, conduct research that has genuinely advanced human understanding of climate, geology, and biology. The Antarctic Treaty System has managed the continent's governance with a degree of international cooperation that is remarkable given the political history of the 20th century. Antarctica does not have a colony. It has rotating research stations. The distinction is not about size or duration or the quality of the people who go there. It is about economic logic. Research stations are funded by institutions that have decided the scientific value of the work justifies the cost of maintaining a human presence. The people there are on assignments. They rotate back to their home countries. They do not raise families at the station. They do not build a local economy. They do not establish governance institutions that persist beyond the mission. When the funding changes or the scientific priorities shift, the station population changes accordingly. A colony is different in kind. A colony is a settlement that intends to persist and grow and eventually sustain itself regardless of what happens to the institution that originally funded it. A colony has economic activity that generates local value. It has governance that derives legitimacy from the community it governs. It has a population that reproduces and raises the next generation inside it. It has, eventually, a reason to exist that is internally generated rather than externally imposed. The question for Mars is what that reason would be. The proposals that appear most frequently are mining, scientific research, manufacturing in low gravity or vacuum conditions, and the insurance argument. The idea that a second planetary home for humanity reduces the risk of civilizational extinction from a catastrophic event on Earth. Mining on Mars is real in principle. The planet has mineral resources, and some of those resources are potentially valuable. But the economics of extracting materials from Mars and returning them to Earth face a significant challenge even in optimistic scenarios. Because the cost of transportation from Mars to Earth is enormous, and the value of most minerals that Mars might have is not high enough to justify that cost when the same minerals are available on Earth or on the Moon or in the asteroid belt at lower logistical cost. There may be specific materials or specific circumstances that change this equation. The general case has not been made convincingly. Scientific research is genuinely valuable, and Mars has scientific questions worth investigating. But science does not generate the kind of economic return that sustains a growing colony. Scientific funding comes from governments and institutions motivated by the value of knowledge, which is real, but which does not scale with colony population the way a commercial economy does. The insurance argument is philosophically compelling and practically limited as an economic driver. A second human settlement elsewhere in the solar system does reduce the risk of human extinction from a single catastrophic event. This is a real benefit to humanity as a whole, but it is a public good, a benefit that accrues to everyone without any individual entity being able to capture its value commercially. Public goods do not naturally attract the private investment that a self-sustaining colony would require. Here is the honest version of where Mars stands right now against the question of economic logic. Antarctica never found its gold rush. Nobody discovered a resource there that made individual people wealthy enough to go in large numbers without institutional support. The result is a continent with a 100-year history of human presence and not a single permanent settlement. California found its gold rush, and within a generation had become something that could sustain itself and then some. Mars is currently looking for its reason. The animations show the destination. The rocket timelines show the delivery system. What neither of them shows is the economic logic that would make Mars, over time, a place where people go because going makes sense in the way that going to California made sense in 1849. That logic might exist. There are scenarios where specific technologies, specific resources, or specific geopolitical circumstances create a reason that does not currently exist in clear form. The development process itself, the engineering advances required to make Mars habitation practical, may generate economic value through spin-off technologies and capabilities that we cannot fully anticipate from here. These arguments are not unreasonable. They are also not yet proven, and the honest difference between a base and a colony is exactly that gap between funded and self-sustaining, between the external decision to maintain a presence and the internal logic that makes the presence worth maintaining on its own terms. A base can survive on meaning, on the idea that it represents something important about human ambition and the future of the species. Meaning is real and it motivates real investment. The Apollo program ran on meaning for nearly a decade and produced genuine scientific and technological value in the process. But meaning is not a business model. Meaning changes when administrations change and budgets get cut, and the next new thing arrives to capture the public imagination. A civilization needs something more durable than meaning to keep paying its own bills across generations. Right now, nobody has built the thing that Mars could offer to make that economic logic work. That is not a reason not to go. It is a reason to be honest about what kind of enterprise Mars colonization actually is, which is not a commercial venture in any currently proven sense, and not a scientific program in the self-sustaining sense, and not an insurance policy in any economically capturable sense. It is a civilization-building project without the economic foundation that has underlain every successful civilization-building project in human history. The gold rush got California started because the gold was real, and the value was clear, and the individual decision to go made sense. Mars colonization at the civilizational scale will need its equivalent, and until someone finds it, the most accurate description of what is currently happening is preparation for colonization, which is a meaningful and necessary thing, but is a different thing from colonization itself. And understanding the difference matters enormously for thinking clearly about what comes next. A base can be funded, a civilization has to make sense, and right now, The sense-making is still ahead of us. There is a photograph taken on the 14th of December, 1972, of a man named Harrison Schmitt standing on the surface of the moon near a boulder field in a valley called Taurus Littrow. Schmitt is a geologist, the only professional scientist to walk on the moon during the Apollo program, and in the photograph he is doing what geologists do, examining rock, reading the story written in stone by processes that happened billions of years before any human being existed to witness them. Schmitt was born in Santa Rita, New Mexico. In 1935, he grew up on Earth. He went to school on Earth. He trained on Earth. He traveled to the moon as an adult, spent 3 days there, and came home. The moon was a place he visited. Earth was the place that made him. Now imagine a child born on Mars. Not a thought experiment. Not a science fiction premise. A specific human being. Born in a pressurized habitat to parents who traveled there as adults from a planet that is now, at its closest approach, 56 million kilometers away. This child has never breathed air that was not produced by a machine, has never felt rain, has never stood under an open sky, has never experienced the gravity that shaped every physiological system in every human body that has ever lived. The gravity that pulled fluid through the circulatory system in a particular direction, that loaded bones with a particular force, that told the vestibular system which way was down, in the way all human vestibular systems have been told since the species began. This child's bones developed in 38% of that gravity. Their cardiovascular system adapted to it. Their muscles built themselves around it. Their entire physical architecture was constructed by the same developmental processes that build every human body. But those processes operated in an environment that no human body has ever been built in before. Can this child visit Earth? The honest answer is that we do not know. We do not know because no child has ever developed from conception through infancy through childhood in partial gravity, and we have no data on what that does to the resulting physiology. We have models. We have extrapolations from the microgravity data accumulated on the International Space Station. We have theoretical frameworks for how bone density and cardiovascular architecture and muscle development respond to different gravitational loading environments. What we do not have is a child who grew up in 38% gravity and then attempted to function in 100% gravity, and whose experience tells us whether the transition is difficult. Impossible, or somewhere in between. If the transition is possible but hard, then Mars-born people who want to visit Earth face a period of difficult physiological adaptation, something like the reverse of what Earth-born astronauts experience returning from long missions in space. But potentially more fundamental, if the transition is possible only with significant medical intervention, then visiting Earth becomes a medical undertaking that not everyone can safely complete. If the transition is not reliably possible, then a child born on Mars may never be able to live on the planet their parents came from. That last possibility is not science fiction speculation. It is a real uncertainty that no amount of mission planning can currently resolve, because the data required to resolve it cannot exist until someone has actually done the thing. The first child born on Mars will not arrive into a world where this question has been answered. They will arrive into a world where they are part of the answer, and they will live their entire life inside the experiment that their birth began. This raises a question that the mission planning documents and the SpaceX timelines and the NASA architecture studies do not address directly, because it is not a question that engineering can answer. It is a question about what it means to bring a person into a situation they did not choose and cannot change. Every human being born on Earth was born into circumstances they did not choose. No one consents to being born. Children are brought into environments their parents chose for reasons that had nothing to do with the child's preferences, because the child did not yet exist to have preferences. This is the universal condition of human reproduction. But the specific features of being born on Mars introduce dimensions that have no parallel in any birth circumstance that has previously existed. The child born on Mars is born into an environment where their physical survival depends entirely on the continuous correct functioning of machines built by other people for purposes that preceded their existence. They are born into a community of a few dozen or a few hundred people. With no access to the broader human world except through communication systems that impose a minimum 24-minute round-trip delay, they are born, potentially, into a body that cannot easily visit the planet where their parents came from and where the overwhelming majority of humanity lives. We also do not know what pregnancy and early development look like in the Mars radiation environment. Human reproduction has never been attempted under the specific combination of cosmic ray exposure and partial gravity that characterizes the Martian surface. The effects of chronic radiation on the reproductive system and on fetal development are understood in some contexts from terrestrial medical experience with radiation therapy and occupational exposure. But the sustained, whole-body, years-long radiation environment of Mars, surface habitation is a different thing from those contexts. And the honest answer to what it means for pregnancy and infant development is that we do not yet know. The precautionary position is straightforward. We should not attempt human reproduction on Mars until we understand what we are exposing the developing person to. The counterposition is equally straightforward. We cannot understand what we are exposing the developing person to without attempting it. There is no laboratory that can fully simulate the Mars environment over the course of a pregnancy. The question cannot be answered without doing the thing. This is the situation in which the first pregnant person on Mars will find themselves, attempting something for which there is no precedent, no established medical protocol based on human data, and no certain knowledge of the outcome, and the child they carry will have no say in any of it, which is true of every pregnancy everywhere. Except that here, the unknowns are more fundamental, and the inability to change course once the process is underway is more absolute. There is also the question of what we are asking of a child who grows up on Mars in a community that needs them. A Mars colony is not a static institution. It is a living system that requires continuous human input to survive, and a system that loses population faster than it gains. It does not persist. The children of the colony are not just people. They are the colony's continuity. Its future engineers and doctors and farmers and decision-makers. The colony needs them to be healthy, capable, committed, and present. What does it mean to raise a child in a place where their presence is, on some level, a resource the community depends on? What does it mean for their sense of choice, of the possibility of a life defined by their own desires rather than the needs of the habitat they were born in? A child who wants to leave Mars cannot simply walk away. They can leave only if a spacecraft is available. And spacecraft operate on 26-month launch windows, and the transit takes 7 months. And the physiological challenge of returning to Earth may be significant. The practical barriers to leaving are not social or cultural. They are physical and logistical in a way that has no precedent in any community that has previously existed on Earth. The first child born on Mars will be a person, specific, individual, unrepeatable, the way all people are. They will have a name. They will have preferences and fears and a sense of humour. They will know things about Mars that no Earth-born person knows from lived experience, because they will have lived there from before they had memories, and the hum of the life support fan will be as natural to them as the sound of rain was to their parents. They will also be the first data point in a study that nobody formally designed. And they will not be a data point. They will be a person, living a life, in the only world they have ever known. The first child born on Mars will not be a symbol of human triumph over an impossible environment. They will be a human being born inside a promise we may not yet know how to keep, in a place they never chose, and they will deserve everything we can give them, which on Mars will never quite be enough and will have to be enough anyway. On the 4th of July, 1876, the United States celebrated the 100th anniversary of its founding, with a World's Fair in Philadelphia that drew nearly 10 million visitors. The exhibits showcased American industrial achievement, the artifacts of a civilization that had, in 100 years, transformed itself from a string of coastal settlements into a continental power. The people who attended that exposition were almost entirely the descendants of people who had come from somewhere else. They had built something new, but the connection to where they came from was still present, embedded in surnames and food traditions and stories that families told about who they were and where they had started. The psychological and cultural distance between the American colonies and Britain in 1776 was the product of 168 years of physical separation. The generation that declared independence had, for the most part, never been to Britain. Their grandparents had, but they themselves knew it primarily as a distant authority that made decisions affecting their lives without adequate understanding of their actual circumstances. The distance between Earth and a mature Mars colony will be greater than this, in ways that are both physical and fundamental. The communication reality is not merely an inconvenience. It is a structural feature of what it means to exist on Mars. A signal takes between 3 and 22 minutes to cross the distance between the two planets. One way, real-time conversation is not possible on any day, at any orbital alignment, ever. The relationship between a Mars colony and Earth will never include a phone call in the sense that every human relationship since the telephone was invented has been able to include. It will include exchanges of messages, careful and composed and delayed, in ways that change the nature of connection fundamentally. For the first generation of Mars colonists, the ones who arrived as adults from Earth, this loss is a deprivation they are aware of. They remember what real-time conversation felt like. They know what they are missing. They carry the grief of that distance with them. For the second generation, the children who grew up on Mars, it is not a loss. It is simply how things work. Earth is a place known from screens and delayed messages and the stories their parents tell, which are already the stories of people who left and cannot fully describe a place to someone who has never been there and may never go. Earth becomes, for a Mars-born person, something closer to what ancient Rome is for a modern American, a place of origin in a genealogical sense, a reference point for history, not a home. A person who grows up on Mars grows up without outdoor spaces in any sense their Earth-born parents would recognize. No parks, no fields, no forests. No beaches accessible without life support equipment that can fail and would kill you if it did. The natural world, which has been the context for virtually all of human cultural and religious and aesthetic development throughout history, is inaccessible without machinery. The Mars-born person's relationship to nature is through glass and sensors and carefully managed excursions, not through the unrestricted physical contact that has shaped human psychology and culture for as long as human beings have existed. What this produces over generations, in terms of personality and values and political sensibility, is genuinely unknown. What is predictable, because it is the consistent pattern of every separated human community in history, is that the people of Mars will eventually stop thinking of themselves primarily as the people of Earth who happen to live on Mars. They will start thinking of themselves as people of a place, with the specific loyalties and specific sense of identity that belonging to a place produces. When that happens, the relationship between Mars and Earth will need new language and new frameworks. Not because the Mars community is ungrateful or the Earth institutions are unreasonable, but because the framework adequate for a sponsored exploration mission will not be adequate for two distinct human communities negotiating a relationship across a distance that takes 7 months to cross and cannot be reduced. Every colony in history eventually stopped being an extension of the place that created it. Mars will be no different, except that the separation will be written not just in kilometers but in generations of people who were born somewhere their parents had never been, who grew up in a world their grandparents built but could not have imagined inhabiting, and who became something new in a place that demanded newness in exchange for the right to exist there at all. That is not a warning. It is not a reason not to go. It is the human part of the human enterprise, the part where the people who went to Mars stop being visitors and start being inhabitants, and where the civilization that sent them has to decide what kind of relationship it wants with the community it helped create hundreds of millions of kilometers away. The distance we never talk about is not the one between the planets. It is the one between what Mars colonization starts as and what it eventually becomes. And that distance may be the greatest one of all. There is a question that sits underneath every conversation about Mars colonization. Underneath the rocket timelines and the mission architectures and the life support specifications and the governance frameworks and all of the other technical and institutional discussions that fill the literature and the conference rooms and the press releases, it is the question the title of this film promised to answer. And it is the question that 18 chapters of evidence have been building toward. What is actually stopping us? The easy answers have been given many times, and they are not wrong. Exactly. But they are incomplete in a way that makes them misleading. Radiation, distance, cost, the difficulty of landing heavy payloads, the absence of breathable air, the contaminated soil, the psychological challenges of extreme isolation. Each of these is real. Each represents a genuine obstacle that requires genuine solutions before any permanent human presence on Mars is possible. None of them, individually, is the answer. The harder answer requires sitting with something that is uncomfortable for a civilization that has, over the past few centuries, developed a deep and largely justified confidence in its ability to solve problems one at a time. The harder answer is that the obstacle to Mars colonization is not any single problem. It is the relationship between all the problems. Follow the logic carefully, because this is the thing that almost never gets said plainly. Air requires power. Without electricity, the oxygen production system does not run. The carbon dioxide scrubbers do not run. The pressure regulation system does not run. People die within hours. So before you can breathe, you need power. Power requires maintenance. The solar panels degrade and need cleaning and eventually replacement. The nuclear reactor has components that wear and require servicing. The battery storage system loses capacity over charge cycles. The distribution network develops faults. Without maintenance, power systems fail. And when power fails, air fails. Maintenance requires spare parts. Every component that wears or fails needs a replacement. The replacement needs to be the right part, in the right condition, available at the moment it is needed. Without spare parts, maintenance cannot be completed. Without maintenance, power fails. Without power, air fails. Spare parts require manufacturing. Some parts can be brought from Earth, but the transit time is months. The launch windows come every 26 months. The cost is enormous. And the parts that fail are not always the parts that were predicted to fail on the schedule that was predicted. A colony that depends entirely on Earth for its spare parts is a colony whose survival is permanently hostage to a supply chain it cannot control. So parts need to be manufactured locally. And manufacturing requires materials. Materials require mining and processing. The raw materials for manufacturing exist on Mars, in the regolith, in the ice deposits, in the atmosphere. Extracting them, purifying them, converting them into feedstock for fabrication processes requires industrial infrastructure, drills and processors and chemical plants and quality assurance systems, which require power, which requires maintenance, which requires spare parts, which requires manufacturing, which requires materials. Air requires power. Power requires maintenance. Maintenance requires spare parts. Spare parts require manufacturing. Manufacturing requires materials. Materials require mining. Mining requires machines. Machines require humans. Humans require air. The loop is complete. And the loop has to be running before it can sustain the people who are trying to start it. Now add the dimensions that are not engineering problems at all. Children require medicine. Medicine requires a supply chain. A supply chain requires governance. Governance requires legitimacy. Legitimacy requires that the people being governed have meaningful participation in the structures that govern them. Meaningful participation requires institutions. Institutions require time to develop and shared experience to sustain. Shared experience is built by a community that has been together long enough to develop common values and common practices. A community that has been together long enough is one whose founding members are aging and being replaced by people born there who have a different relationship to the project than the people who chose to come. This is civilization, not a metaphor for civilization, actual civilization, with all of its slowness and complexity and irreducibility to engineering specifications. The thing that Mars colonization eventually requires is not a better rocket, or a more efficient life support system, or a more robust spare parts inventory, though it requires all of those things too. What it ultimately requires is the capacity to build a civilization from scratch, on a 26-month resupply schedule, in an environment that provides none of the background conditions that every previous human civilization was built inside of. No civilization in human history was built without inheriting a vast web of prior knowledge, tools, ecology, and institutions from what came before it. Agricultural civilizations built on knowledge accumulated by hunter-gatherer societies that preceded them. Industrial civilizations built on the agricultural and trading societies that preceded them. Every civilization that has ever existed was assembled from pieces that already existed, adapted and extended by the people who built on top of them. The first Mars civilization will not have that luxury in the same way. It will have Earth, 400 million kilometers away at maximum separation, accessible on a 26-month schedule, able to send expertise and components and goodwill, but unable to be physically present when the situations arise that require physical presence. It will have the knowledge that its founders carried with them, which is enormous by any historical standard and still a tiny fraction of what Earth civilization actually contains. And it will have the people who are there, doing the work, in the habitat, facing the problems that arise on the schedule that they arise on, which will not be the schedule that anyone planned. Much of the engineering required for Mars colonization is understood in principle. What is not yet proven is the closed loop at the scale, reliability, and duration that permanent habitation requires. The systems work in laboratories. The systems work in demonstrations. The systems have not been run together, simultaneously, for years, in actual Martian conditions, supporting actual human beings who cannot leave when the experiment is over. That gap, between understood in principle and proven in practice at civilizational scale, is the honest location of where we are right now. Mars is not impossible. The people who say it is are wrong. The physics permits it. The chemistry permits it. The biology, as best we currently understand it, does not rule it out. There is a path from here to a permanent human presence on Mars, and meaningful progress is being made along that path in real time. But Mars is brutally honest in a way that our imagination has not yet caught up with. It removes every gift Earth has been giving us for free, and then presents the invoice without apology. It does not care about timelines or press releases or the emotional need for the answer to be simpler than it is. A colony on Mars will not fail because one problem proved unsolvable. It will succeed or fail based on whether a small group of human beings, far from everything that built them, can keep a loop running that has never run before, in an environment that has never supported a living thing, while simultaneously building the institutions and knowledge and relationships that will allow the next generation born there to keep it running after them. That is not an engineering problem. That is not a funding problem. That is not a political problem. Though it is all of those things too. That is the oldest human problem there is. Figuring out how to make something last in a place that is trying. Not maliciously, but with complete indifference. To stop it. We are not waiting for one rocket big enough to carry us to Mars. We are waiting for a civilization mature enough to understand what it must carry with it, and honest enough to admit what it does not yet know how to build, and brave enough to go anyway. That may be the most human thing about the whole enterprise. We are going anyway. We have always gone anyway. Into the cold, across the ocean, over the mountains, into the places that were not ready to receive us, and that we were not ready to inhabit. We have paid the cost of going before we were ready, many times, in lives and suffering and long stretches of failure before anything that could be called success. Mars will cost something. The question is not whether to pay. The question is whether we understand clearly enough what we are paying for, and what we are paying with, and whether what comes after the payment is worth the price. and we are definitely further from being ready than we feel when we watch a rocket leave the ground and believe, for the duration of its ascent, that going is the same as arriving. Step outside. If you are able to, actually step outside. Open a door or a window and let what is out there come in. Feel whatever temperature the air is. Feel whatever humidity. If it is raining, feel the rain. If the sun is out, let it land on your face for a moment. Breathe. You just did something that no human being on Mars can do. You interacted directly with the atmosphere of your planet, the one your biology was built for, the one that has been maintained in breathable condition for 4 billion years by processes so complex and so ancient and so thoroughly distributed across the entire surface and ocean and atmosphere of the world that no complete accounting of them has ever been made and probably none ever will be. You did not earn that breath. You did not build the system that made it available. You were born into it. The way you were born into your language and your gravity, and the orbit that keeps you at exactly the right distance from a star producing energy, at exactly the rate that biological life can use. You inherited all of it. Every living thing that has ever existed on this planet inherited all of it. The inheritance is so total and so constant that it is invisible. The way the deepest assumptions of any culture are invisible to the people living inside it, because there is no contrast case, no alternative reality that makes the inherited reality visible as a specific thing rather than just as the way things are. Mars is the contrast case. Everything that seems like background on Earth, that seems like the neutral, unremarkable condition of existence rather than a specific and remarkable gift, reveals itself as exactly that. The moment you try to survive without it, the atmospheric pressure that keeps your blood from vaporizing, the magnetic field that deflects the charged particles that would otherwise damage your DNA continuously and cumulatively across your entire life, the gravitational field that your circulatory system and skeletal system and vestibular system were designed around by 4 billion years of trial and error, the biological community in the soil that makes food production possible without industrial chemistry, the water cycle that delivers clean, fresh water to continental interiors without any infrastructure at all, the temperature range maintained by the greenhouse effect and the ocean heat buffer that keeps liquid water stable across most of the planetary surface. Every one of these things is a system, a physical or chemical or biological system, operating continuously, at planetary scale, for time scales that dwarf the entire history of human civilization. Every one of these systems is something that a Mars colony has to replace, partially or entirely, with engineered infrastructure designed by human beings working on timescales measured in decades, building on knowledge that is comprehensive by human standards and still radically incomplete by the standards of what the systems being replaced actually do. This is what Mars teaches, not as a lesson handed down, but as a fact that emerges when you look carefully at what colonization actually requires. It does not teach that Earth is fragile. Though Earth is fragile in ways that deserve serious attention, it does not teach that humanity should stay home, though the cost of not staying home is real and should be counted honestly. What it teaches is that Earth is an engineering project of such sophistication and such antiquity that the civilization currently living inside it has no hope of fully replicating it on any timescale relevant to any individual human life, or any current institutional planning horizon. The atmosphere did not happen in a decade. The soil ecology did not happen in a century. The magnetic field is the product of processes running since the planet formed. The water cycle has been operating in something like its current form for more than 3 billion years. The combination of all of these things into a stable, self-regulating, mutually reinforcing system that maintains conditions suitable for biological life is not an accident and not a given. It is the result of a process so long and so complex that we have only begun to understand the outlines of how it works. Mars colonization forces a reckoning with this inheritance, not because it threatens to destroy it, though the same civilization planning to colonize Mars is also, through other activities, stressing the Earth systems that make life possible in ways that deserve at least as much attention and engineering ingenuity as the Mars program receives, but because the act of trying to build what Earth provides, on a different planet, with finite resources and human lifetimes, and the full force of physical constraints that admit no exceptions, makes visible just how much is being provided. The air is a machine on Mars. On Earth, the air is what the machine is trying to produce. The water is infrastructure on Mars. On Earth, the water is what the infrastructure is trying to deliver. The soil is a fabrication challenge on Mars. On Earth, the soil is the result of 4 billion years of biology doing what biology does, building complexity from chemistry, building life from complexity, building soil from life, building food from soil, building the animal that is now standing somewhere on Earth, breathing without thinking about it. The Mars program is, among many other things, the most expensive and most serious audit of Earth services ever conducted. Every line item in the Mars life support budget is a line item on an invoice that Earth has never sent. Because Earth is not in the business of sending invoices. Because the services it provides are older than the concept of payment and more fundamental than any economic framework. We have been living on credit for the entire history of our species. The credit comes from a planetary account that was funded before we existed and that we have never been asked to repay. Mars forces, for the first time, to look at the itemized bill and understand what we have been given. None of that diminishes the case for going. The attempt to understand what we must carry to Mars is also an attempt to understand what we carry on Earth without knowing it. That attempt is worth making. The destination is worth the cost. If the cost is counted honestly, and the attempt is made with clear eyes about what it requires and how far we still have to go, the closer we get to Mars, the more we realize that Earth was never just the place beneath our feet. It was the life support system we were born inside. So complete, so ancient, so quietly competent that we mistook it for background. It gave us air and called it weather. It gave us water and called it rain. It gave us soil and called it ground. It gave us gravity and called it down. It gave us a sky that protects and called it blue. Mars may one day teach us how to leave home. It is already teaching us something more valuable. It is teaching us what home actually was, what it has always been, and what we carry inside us from having been born here, on the only planet in the known universe that has ever, in 4 billion years of trying, managed to keep something alive long enough to look up and wonder what is out there. That is what Earth has been doing for us all along.